Here is the problem. We have a car driving on a bumpy road. The car body has mass m and sits on a spring with a spring constant c. There is also a hydraulic cylinder with a surface area A that can push the body up or down. An electrohydraulic converter takes an input voltage U and creates a pressure difference delta P equals K times U. The goal of the system is to keep the car body steady, meaning displacement x should stay close to zero even when the road surface height h changes. We need to do three things: identify the input, output, and disturbance signals, write the differential equation, and draw the block diagram. Let us start with part A, identifying the signals. What can be controlled? The voltage U going into the electrohydraulic converter. That is our input signal. What do we want to measure or regulate? The displacement x of the car body. That is our output signal. What is the external disturbance we cannot control? The bumpiness of the road, which is the height h. That is our disturbance signal. So to summarize, input is U, output is x, disturbance is h. Now part B, the differential equation. We use Newton's second law. The sum of all forces on the car body equals mass times acceleration. Let us write m times x double dot equals the sum of forces, F sigma. What forces act on the car body? Three forces. First, the spring force. The spring connects the car body to the wheel. When the road goes up by h and the body moves up by x, the spring compression is h minus x, so the spring force is c times h minus x. Second, the hydraulic cylinder force. The cylinder pushes with a force equal to the pressure difference times the surface area, A times delta P, and we know delta P equals K times U, so the cylinder force is A times K times U. Third, gravity pulls down with force m times g, and the spring rest position already accounts for gravity. So when we write the spring force as c times h minus x, gravity cancels out. Putting it all together, m times x double dot equals c times the quantity h minus x plus a times k times u. Let us expand. M times x double dot equals c times h minus c times x plus a times k times u. This is our differential equation. Notice it has two inputs, the disturbance h from the road and the control input u from the voltage. The output is x, the displacement. Let us rearrange. M times x double dot plus c times x equals c times h plus a times k times u. To build the block diagram, we need to express x in terms of integrals. From the equation x double dot equals 1 over m times the quantity c times h minus c times x plus a times k times u. If we integrate x double dot once, we get x dot, the velocity. If we integrate again, we get x, the displacement. So we need two integrators in our block diagram. The first integrator takes the acceleration and gives velocity. The second takes velocity and gives displacement. Now let us draw the block diagram step by step. Start from the left. The input voltage U goes through a block K, giving delta P, then through a block A, giving the cylinder force A times delta P. This force enters a summing junction. The road disturbance H goes through a block C, giving the spring force from the road, C times H. This also enters the summing junction as a positive input. The spring force from the body displacement is C times X. This enters as a negative feedback, minus c times x. The sum of these forces is F sigma. F sigma goes through a block 1 over m, giving the acceleration. Then through the first integrator, giving velocity. Then through the second integrator, giving the output x. Finally, x feeds back through a block C to create the negative spring force feedback. Let us review what we did. We started with the physical system. A car on a bumpy road with a spring and hydraulic actuator. We identified 3 signals: input voltage U, output displacement X, and disturbance road height H. We applied Newton's second law to write the differential equation: mx double dot equals c times h minus x plus AKU. And we translated this equation into a block diagram with 2 integrators, a feedback loop for the spring, and 2 input paths for the control voltage and the road disturbance. This is a complete plant model ready for controller design.